It's a bit like a fine horse. It's very highly strung. It's good when it goes, but sometimes it's going to buck you off.
Yep. You're listening to the Cosmic Cast. Hello and welcome back to the Cosmic Cast. I'm John Penney-Fisher, and we've got the in-house team this week of Marissa Lowe.
Hello.
Tom Harvey.
You're right.
And our sound engineer, who you often hear in the background chortling to himself, Elliot Carter.
Hello.
How's it going?
Yeah, it's all right.
How do you feel being this side of the microphone for a change?
It's a little odd. I feel exposed.
I didn't know you could talk. I'm amazed.
Neither did I until this moment. I've been quite worried.
So, Elliot, in fact, you're a PhD student here.
Yeah,
and
I am
in your
indeed.
final year, no?
Yeah, rabbit in the headlights time.
Rabbit in the headlights time.
Yeah, so my PhD is on using halogens and noble gases to trace fluids and maybe magmatic things in ophiolites.
The old halogen bandwagon. Very good.
I'm one of those.
So it's but mostly terrestrial then. You're not.
Yes,
You're not extraterrestrial.
I keep firmly earthbound.
Mm-hmm. Yeah.
So let's break that down. What are halogens?
So halogens are the seventh group of the periodic table, from fluorine to iodine, and then another one that's really unstable that I don't know. But so they're like things that make salts. They're very mobile in fluids, and they've got like really strong fractionations between different things in the surface, like seawater or like sedimentary fluids, things like that. So they're really good for tracing fluids that were once at the surface or might have come from the surface in other things.
And would you mind explaining what an ophiolite is?
Yeah, this is like every abstract I have to write.
Yeah.
And next is so an ophiolite is a section of oceanic crust, so that's the very outer layer of the Earth, and usually some mantle attached to the underneath. That's the mantle's the next layer of the Earth inwards, and they're kind of glitches almost in tectonics. So they're little slivers that end up on top of a continent, most often during some kind of collision during a subduction zone. So a subduction zone comes along, and maybe for some reason something that would have gone down slivers up over the top of the continent.
Yeah.
But what that means is you then have something that should be 10 kilometers maybe down in the mantle that's now at the surface, and you can look at it. So those and things called xenoliths are like the only direct samples we have of the mantle, so they're really super useful.
That's really cool. How many ophiolites are there on Earth?
That's a very good question. I have no idea the answer.
I suppose famously there's the lizard in Cornwall.
Yes.
There's one in Cyprus.
The
Troodos
Troodos intrusion is where a lot of undergrad field trips seem to go. I guess it's
That's a fantastic
and Oman is the
field
other
trip.
really famous one.
Oh yes,
We've got
indeed.
one
That's
more.
very fresh, isn't it? Is that why it's so well studied?
Yeah, and I think part of it is the early models were... It's the biggest apart from anything else. I think it's very well exposed, and people have just been studying it for years and years and years. And early models, and there's still a lot of argument about this, with like it's very true to being a mid-ocean ridge crust situation. So it's exactly what you form, say, at the middle of the Atlantic or the middle of the Pacific. A lot of people argue with that and say there's a lot of influence from the subduction zone, but that's maybe partly why it has received so much attention. I don't really know the history of exactly why.
So where are your samples from?
Some of them are from Oman.
Right. So you got a mixed bag of ophiolites, have you?
Yeah, so I started off looking at one called Lika in Norway, which is a little bit less well known, and then I got involved with a drilling project in Oman, which has retrieved these drill cores from sort of about 400 meters below the surface. And what's really cool about these is, so Oman is mostly a desert. A lot of stuff that might degrade in hot temperatures does, and things get sort of washed away, and you only have what's exposed at the surface that's getting a bit weathered. Whereas these have a sort of full core through all the things, including stuff that's like softer, lots of minerals that might have been totally weathered away at the surface. So they're kind of a lot less biased and a lot less weathered. So really cool.
Ophiolites are typically very altered, is that right? From the way that they would be if they were, pre-subducted crust.
I think that is one of the huge arguments about Oman.
Right.
To what extent has being near a subduction zone during putting it onto the continent altered it, or was it ever formed at a real mid-ocean ridge?
Mm-hmm.
And it's not really an argument I'm hugely in.
Mm-hmm.
I couldn't. I would say there is a big subduction influence, but some people would say there isn't.
Yeah, but so when you're looking at your like halogen traces, do you have to like account for alteration of the rock that might have affected that? Because you're looking at like mantle processes, is that right?
Yeah, absolutely. Yeah, so especially what I'm looking at Lika, there's these channels of things crossing the mantle section that we're pretty sure are to do with subduction-related fluids and melts percolating through the mantle. So yeah, what I've really focused on there is untangling subduction signatures from signatures that are to do with water coming in from seawater above.
Oh, that's really cool.
And halogens, you can do this because seawater has distinct halogen ratios versus mantle. Is that the idea?
Seawater is very different from mantle, and mantle's very depleted, so it won't give much of a signal. The moment you've got some seawater, that's what you'll see. And then the sort of things that come out of subduction zones mostly were once seawater, but they've been fractionated by being incorporated into minerals and then released again out of minerals, or by being involved in sediments and things like that.
It seems quite challenging, though. I guess also the big thing about... Well, because halogens are only present in really low concentrations in the first place, aren't they? So trying to measure these things well must be difficult.
Yeah, so we've got quite a cool method here at Manchester, one of only a handful of labs in the world that do it. So it's basically an extension of argon-argon dating, if anyone's heard of that. So what we do is we prepare a small amount of sample, wrap it up in tin foil, and we send that off to a nuclear reactor and bombard it for about 24 hours with neutrons. And what that does is it actually causes nuclear reactions so that elements like chlorine, potassium, so a lot of our halogens, but also potassium, convert into noble gases. A small proportion of them convert. And we include various monitors where we know exactly the concentrations of these things in, along with our samples, and then we measure everything on a noble gas mass spectrometer. So what we might measure is an isotope of argon, and then through a series of back calculations, we work out how much chlorine has been produced to give you that much argon.
Yeah, it's a very clever method.
It is. It's sort of surprising almost that it works. Because it's...
Well, particularly, so the concentrations we're dealing here with are parts per billion. So it's one atom of a halogen in a billion atoms even. I mean, that's...
Yeah, absolutely. It's astonishing, really. And you can do that on 5 milligrams of sample, so 5,000th of or even less. I've run like 1 milligram of something, and you can see the halogens.
So how do the noble gases you've been measuring fit into this picture?
I think so. They're quite similar in a way. The noble gases, they're good tracers of fluid processes because they tend to end up in the fluid if there are any there. You know, if you've got a solid in contact with a fluid, you'll get a lot of the noble gases going into that fluid. And again, you have isotope ratios that vary between all the different things you might be interested in terms of the mantle. Basically, involvement with sediments can fractionate the abundances of noble gases from one another, so that you end up with the heavier noble gases being more abundant than the lighter ones.
I think what's nice about this project really is it really sort of demonstrates how geochemistry is a tool to investigate different processes that happen on the Earth, really. Or you're looking at different systems and different elements that tell you different things and then piecing a story together, really. Yeah,
and it's quite hard, but I guess that's the point. Yeah, I was looking at my data set for Lika recently. I've got like 150 different single step analyses and trying to combine those all together on loads of different minerals and extract it in different ways and trying to like pull a story out of that has been quite challenging, but I think I've getting there at least.
So what do your samples look like when you get them? If they're using such small masses for each analysis, do you just kind of get like a hand specimen sized rock, or do you get...
So what I have generally done, and partly because of what you're saying about how these things have lots of alteration processes and other things going on, is to take them apart into their individual minerals. So in many cases, like one mineral might tell you about one process, but a different mineral tells you about another. So mainly what I've been studying is these things called peridotites, which make up most of the mantle on Earth. And these are mostly olivine, which is a magnesium-rich silicate mineral. So olivine's sort of the primary mineral, but then that gets altered to serpentine when it reacts with water. So one thing I've done is to try and pick out totally fresh olivine with no serpentine attached to it, which was really hard, took hours and hours and hours, but those show a completely different halogen signature to the serpentine they're associated with. So we're able to show like some event that looks like it's subduction related prior to these things being serpentinized. So that puts quite an important like age constraint on when the alteration of the ophiolite happened. It had to happen after there's some kind of subduction related events. So it's not like a pure seafall process. It's not happening way out in the ocean. It's happening near a subduction zone, near the ocean, near the continental margins.
So what are the main instruments that you use here in Manchester to analyse your samples?
I mainly use two noble gas mass spectrometers called Helix and Argus. And I love them dearly.
Oh.
And I'll say no more than that.
Good old Helix and Argus.
Yes, I think the subtext. I don't think it's unreasonable to say we've had a few frustrations in the labs of.
Yeah. I think it's maybe inherent to working with such sort of highly strung machine. It's a bit like a fine horse. It's very highly strung. It's good when it goes, but sometimes it's going to buck you off.
Yeah. No, but I mean, it's true. If these sorts of instruments are frustrating, I mean, how much downtime do you think you've had as a result of instrument failure and because these things are very.
PhD, maybe 12 months.
Mm-hmm.
The point is that technical instrumentation always is going to have some element of downtime in it.
Yeah.
I mean, it seems you talk to pretty much any PhD student that's doing something that involves, I mean, even people doing modelling projects, their computers can not work.
Yeah, or you spend weeks muddling through scripts because there's errors and bugs and things like that.
I'm actually glad to have instrument downtime because otherwise I'd have to admit my failures were entirely my own. So, I'm pretty...
It's the instruments again.
The instruments. Yeah.
One of my friends who's a PhD student at Leicester, she went to South Africa and then the telescope stopped working. So, at least you only have to come into work to find out that the Helix isn't working, for instance.
Well, if you don't mind me asking, are Argus and Helix specialist mass spectrometers then?
So they are quite specialist machines. So other mass spectrometers you might use to measure a whole range of different elements or isotopes. Noble gas machines are just for noble gases. So part of how they work, I believe, is essentially nothing but noble gases much ever goes into the spectrometer, so it stays very clean. You don't have lots of interfering peaks at different masses. So how we do that is we have what's called a preparation line. So we release our sample gas into that line. So it's at high vacuum.
So you heat them using a laser?
Yes, either a laser or crushing. I've used crushing as well, where you can... So what that does is release sort of small pockets of fluid that might be trapped in your minerals. Might tell you something quite different to what's sort of bound up in the main mineral. And then we clean it up with these things called getters. So we expose it to hot charcoal that reacts with a lot of the reactive gases to remove them. And then we input it into our spectrometer. And in case anyone doesn't know what a mass spectrometer does, we ionize our gas. So we form the charged particles and then accelerate them in an electric field. And then they pass through a big magnet. And what that does is it bends the path of each of those ion beams. And what's particularly important is that if things have different masses, they have essentially more momentum, so they're harder to bend. So something with a high mass will go in a slightly straighter line than something with a low mass. And you end up separating out your gases by their mass. So you can measure different isotopes and different gases.
Yeah. And it's incredibly sensitive as well. This is why I guess so many things can go wrong, because when you're then counting these atoms, I mean, you're talking about, in some cases, you're counting handfuls of charged particles at any given time.
I worked out once what proportion in a million would be the thing you're looking at, and a lot of normal geochemical elements, like say magnesium, might be in parts per million. If you work that out for noble gases, it's like parts per trillion or even lower. It's a complete order of magnitude less abundant. And so and that's partly why the halogen method works, because even though you're only converting a small proportion of these things, the noble gas machine is so sensitive that it can pick them up.
Yeah.
So does that contrast quite heavily with doing, for instance, lunar analyses? Because these things, I'm thinking noble gases, there are a lot more of them in lunar samples?
Well, yes, there are more noble gases in terms of raw concentration or abundance than some of the mantle things that Elliot looks at, but you're still talking quite low absolute abundance. I mean, it's still, when you're actually ionizing these things and they're being slung around the mass spectrometer, you're still only measuring, maybe say tens of thousands of counts per second as opposed to maybe like hundreds or thousands of counts per second. So it's still quite sensitive relative to maybe other more routine spectrometer methods that people use in like biochemistry, for instance.
Right.
So, Elliot, you had quite an exciting summer. You were out in Japan.
Yeah, it was.
Whereabouts were you?
So I was in Tokyo. I applied for a Japan Society for the Promotion of Science summer fellowship, and I was lucky enough to get accepted. So I got to spend three months at the University of Tokyo, working in Professor Hirochika Sumino's lab, working on noble gases.
That's very cool. So he's a well-known world expert for noble gas analysis, isn't he?
Yeah, absolutely, and
So
collaborates with our group here.
Yeah.
So I'd met him while he was visiting here to do some analysis on the Argus. And
So what sort of things were you doing? Were you working on ophiolites as well, or are you working on other samples?
yeah, essentially like an ophiolite. So what I was working on was something called the Horoman peridotite, which is in Hokkaido, which is the northernmost island of Japan.
So what is that? It's a lump of peridotite randomly?
Yeah, so it's a big body of peridotite that's been exhumed from around about 50 kilometers down in the mantle.
Subduction related still.
Yeah, so that was what I was kind of investigating. Is what's the setting is thought to be above a subducting plate, so what we call the mantle wedge. So you have a portion of mantle above a subducting plate where water and other volatiles and all sorts of things are being driven off by the heat that the plate going down is feeling, and they sort of alter and pollute the mantle above with things that were once at the surface. So I was looking at what is the signature of that in these rocks. But it's a really cool place. Like, I got to go there on field trip, and yeah, it's just this entire set of mountains entirely made of peridotite.
That must be quite weird.
Yeah, and it's incredibly fresh. Like, I've been studying peridotites for a few years, and everything's usually quite serpentinized. You have to work fairly hard to find the fresh olivine. This is just pure fresh olivine.
Because I guess for listeners who are not too familiar with what fresh peridotites look like, I mean, olivine is a bright green mineral. Its gem name is peridot. It's often used for jewellery and stuff. So to have lumps of quite fresh olivine-bearing rocks must be quite cool.
Yeah, it's really cool. I mean, so the very surface layer is sort of rusty red.
Are they quite
colour.
coarse-grained?
Yeah, some of them are incredibly coarse-grained. So you get these really cool channels of, or we call it sort of mega crystal olivine.
Yeah.
And you have crystals that are centimeters across.
That's awesome.
So those were one of the things I focused on, because in those you have a lot of fluid inclusions that you can see with a microscope. So one of the things I was doing was looking at those under what's called Raman spectroscopy, which is quite good for detecting carbonate and water, so carbon and water peaks. So I was looking at those and was able to find sort of a bunch of carbonate minerals and hydrous minerals. And then taking the same rocks and other ones and crushing them in a noble gas mass spectrometer to look at what the signatures of that were. And what that really showed was, in terms of helium, so helium's quite important when you're looking at the mantle, because pretty much everywhere we look in the upper mantle, we see that it has the same helium isotope, which is same helium isotope ratio, which is about 8 times the atmospheric ratio. And these had exactly that, but in terms of all the other noble gases, they looked very much like the atmosphere. And it didn't matter what proportion of helium you released, or, regardless, you get an atmospheric, not exactly, but close to the atmospheric ratio in, say, argon isotopes. And
so what's that telling you? Is that seawater?
yeah, I think that's what that's telling you, is that these things do have a inherent atmospheric component
That's deriving, or is it sediments maybe even?
Yeah, it could be seawater bound up in minerals. It could be sediments. Halogens would probably be a better discriminant of that, but we didn't have time to be doing all the irradiation and that in 3 months.
Yeah.
But so it's quite important, because these things are 50 kilometers down, so that tells you at least that noble gases are getting that far down into the mantle during. So yeah, I guess to set the scene slightly on this question, some people say there's been work to suggest essentially you can't subduct noble gases; they release too easily and they're just completely returned to the surface. So there's no deep subduction of noble gases and no sort of full Earth cycle of those kinds of volatiles.
Hence why you would expect to see mantle-like helium values.
Yes, even that sort of depth, you might think, okay, no, there's not going to be anything. The other thing is that whenever you have a rock, you inherently get some pollution of you get some contamination by the atmosphere when you expose it to the atmosphere. So a constant problem in noble gas stuff is like, am I seeing just bits of the air that this sample has been in while I've prepared it, clung to it, or am I seeing something that's actually part of the rock? And it's very hard to resolve that.
Because that's an issue for crushing, isn't it? You can get absorption of air onto your samples.
Yeah, but so working that out exactly will be one of the challenges of this. But I think the fact that these things are in proportion to one another and the signature never changed with progressive crushing. So I'm probably going a bit too technical, but I think it's quite important.
Oh, that's interesting. That sounds like quite a lot of work you packed into 3 months then.
Yeah, and in fact, all the noble gas analysis was packed into about 3 weeks.
Wow.
So I ran pretty solidly for 3 weeks.
So did you get much chance to really experience a Japanese lifestyle and what it's like to sort of live in Tokyo for 3 months, or were you literally just getting up, going to the lab, and going back to wherever you were staying?
No, I actually got to have quite a bit of fun. One thing I wasn't really prepared for was it was a big cohort of us out there, so lots of different people from all over the world. So
cool.
Canada, the USA, Sweden, Germany and France, as well as the UK. So about 100 of us scattered all over Japan doing our individual projects, but we were all together for the first 2 weeks. Okay. So it was really nice.
That's nice.
Basically made some friends.
Yeah. So were you just staying on the campus of the university, or were you?
Yes, yeah. I was quite lucky. Some people who were an hour and a half commute out in Tokyo.
Yeah.
Tokyo is a big city. You
Yeah.
can be in central Tokyo and be an hour and a half away. But I was 10 minutes from the lab, which was amazing.
That's cool.
Yeah, in a little flat. It's very cute.
So what did you enjoy about living in Japan?
Probably the food most of all. It's fantastic, and the amount of good food you can get for very little money. I think compared to here, the quality of fast food is, it's not particularly fast food, but you can get amazing ramen for under a tenner. It's the best you've ever had. Yeah.
But that wasn't your first trip to Japan, was it? I think you'd been on a boat previously, hadn't you?
Yes, yeah. I've been twice to as part of the Oman drilling project, which I mentioned earlier. I've been twice out to go on the IODP ship called Chikyu.
So what is that? That's
so it's a drilling ship. So it's a pretty amazing thing.
What does IODP stand for?
Sorry,
it's the
International Ocean Discovery Program.
Right. It's it's American, isn't it? Or is that?
So the ship is American.
Yeah.
The whole program has about 30 member countries, I think.
Okay, right. And it's just for drilling and dredging the ocean floor, isn't it?
Just drilling, in fact. Yeah.
Is it just drilling? Okay.
Yeah, they don't even run dredging. So they have 2 ships. One's called the Joyde's Resolution, which is American. Sorry, I just said Chikyu was American. They have 2 ships. So one is Chikyu, that's owned by the Japanese government, and one's called the JR, Joyde's Resolution, which is, I believe, owned by National Science Federation in the US. So a lot of our climate records come from IODP drilling of deep. So basically I don't know exactly, but I think the ice record goes back a few tens of thousands of years, maybe hundreds of thousands. I'm not sure, but if you want to go back beyond that, you have to look at sediments in the deep basins of the oceans.
But it's basically why we know so much about the ocean floor, basically.
Yes.
And so it's a really important program.
Yeah, and Chikyu's a really cool boat. It's the biggest thing I've ever seen. It's about 100 meters tall, so it's got this big, basically a crane on top of it, sort of crane tower thing, which hoists up the pipes for the drilling, and it's about probably 200 meters long. It's absolutely huge, and it was built to drill to the mantle. It's not done that yet, but that was its.
That's quite something. So because I guess oceans are quite deep, aren't they?
Yes, yeah. So drilling to the mantle is a nightmare of a problem. So at the moment we've got about 2 kilometers into oceanic crust. That's the deepest.
And then oceanic crust is what? Is it 15, 20 kilometers thick?
Normal is 7 plus minus 1.
Okay, so 7 plus minus 1. Right.
So to get into the mantle, you're probably in 2 or 3 kilometers of water. Then you're going into a hole that's probably 6 inches wide at most.
Wow, but that would be amazing to get actual. That would be that's.
It's like the.
It's never
Holy
been
Grail.
achieved, has it?
Yeah,
to extract mantle directly
terrestrial
from
rocks. It's like the Apollo mission. But its trouble is that it's not as exciting to most people, I think, as the Apollo. I think it should be, but it doesn't spark the popular imagination in the same way as going to the moon.
Yeah. Well, I guess you can't see the mantle, can you?
You can't, unless you go to Oman.
Unless you go to Oman. Yeah.
How long were you on this boat then?
First time I went, I was on for a month.
Wow, okay.
It's quite crazy by the time I got off.
But you weren't drilling, were you? You were just
No,
it was just parked up in Japan, wasn't it?
No, so basically it's got amazing labs. So the project, when they recovered all this core, I think it was about 2 kilometers of core in all from Oman. I might be wrong on that. They wanted to characterize it all like they would if it was a ocean-going drilling mission. So they wanted to get sort of full geochemistry, like petrological descriptions. They even CT scanned the entire core. So there's about 10 terabytes of CT data sitting on a hard drive somewhere. But to do that, you can't turn up to some university and say, "Hi, can we use all your labs for 2 months straight?" Like, that wouldn't work. So they sort of hit on the idea. GQ is very expensive to run, so it actually spends a lot of the year not doing that much, because the moment it goes to sea, you're spending millions of pounds on fuel. So unless it has a project, it's not constantly in use.
But it must be hard to do a lot of these analyses on a boat that's constantly moving.
Yeah, well, so I mean, it's so big, it doesn't move that much.
Okay, I can't.
It is very strange, though, running a geochemical lab
on a boat
while it's moving.
I mean, it
because we did go out to
sounds
sea
absurd.
a couple of times for
Yeah.
sort of testing stuff and
Yeah.
like the rocking. Yeah.
I don't know. I guess I've never been on a big cruise ship, so I guess I don't know how stable they are, really.
It's enough to make you feel a bit sick.
Mm.
But yeah, it's the only thing that was a bit scary was sort of acid digestions that were tried.
Mm-hmm. Well, particularly when you're in an earthquake zone as well.
Yeah.
Oh, God.
Yeah.
So, Elliot, you've heard us ask all of our guests this so far, but never answered it yourself.
No, and somehow haven't prepared an answer.
You really never thought about it beforehand? Okay. So, if you were doing something outside of your PhD, either in academia or outside of it, what would you want to do instead?
I think probably something to do with food.
Yeah?
Yeah.
Good answer.
I finished a big bit of work on Wednesday, and the first thing I did was make a pizza from scratch.
Oh, very
'Cause I hadn't
nice.
cooked in
What
about
a
a
way
week,
to
and I was like,
celebrate.
it wasn't very good. It was
What was on the pizza?
what was on it? Grilled aubergines,
Oh, strong start.
pickled chilies.
Oh,
Yeah, you know, like there's the green ones in a jar.
Yeah.
Those chopped up. And that was it. And mozzarella.
oh, lovely.
Interesting.
It was pretty
Not even a
tasty.
tomato base.
Oh yeah, I mean, I thought that went without
Is that
Obviously, there
because-
was a tomato base, John. Obviously.
I'm not a monster. Yeah, so I think actually, yeah, some kind of. I wouldn't want to be a restaurant chef. I think I'd go mad.
Food reviewer for The Observer?
Yeah, that sounds pretty cushy. Yeah.
You could be the next Jay Rayner.
Yeah. Oh, that would actually be really fun. Or like a sort of pop-up, but you do it like once a week. I'm just like, I'll just take the van out, I guess. I don't know. That'd be nice.
I thought you would have said something to do with music, maybe.
Oh, that's a good point, yeah.
'Cause you are
So
a
yeah,
musician.
I like playing.
Yeah, for the listeners out there, Elliot is a wonderful drummer.
Thank you. I'm very loud.
That's exactly the quality you want and need.
Right, that's the most important thing.
Hmm.
Rhythm is very overrated.
Hits all of those drums and in the right order sometimes.
Well, that's
too.
the key point, isn't it? Yeah.
I can hit the most drums at once of anyone I know.
Wow.
Yeah,
How many is that?
2. Yeah, no, I think in some ways it's almost better as a hobby.
Mm-hmm.
'Cause I think if you had to go out every day touring,
Mhm.
you'd quickly hate every song you
Yeah, I think you
ever
probably
played.
would. Yeah, yeah. What drew you to science in the first place?
What drew me to science? I don't know. I think I was quite a geek at school. I
Mhm.
liked science and history, and I sort of practically flipped a coin whether
Mhm.
which one I'd apply to go to uni to do.
Mhm.
I pretty much did that.
Yeah,
Yeah.
me too, actually.
I think actually
Yeah.
geology is quite a good. It's
Yeah.
the one thing where you get to do science and history on a kind of
Just very old history.
yeah, very old history,
Yeah.
but history nonetheless.
Yeah.
Yeah,
Yeah.
I used to be into all those sort of like brief history of time. I'm one of the 3
Mhm.
people who's read the whole thing. Sorry, that sounds really arrogant. I mean, like a lot of people have bought it and never read it. I quite liked it. What was I? Yeah, so I used to be really into popular
Mm.
science books and
Yeah.
all the sort of strange stuff around physics and black holes and
Mhm.
things.
Oh yeah, everyone loves a black hole.
Right, well, thank you for coming to talk to us today, Elliot.
Oh, you're very
And
welcome.
best of luck for the rest of your PhD.
Thanks.
And thank you to everyone listening at home, and see you next week.